तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Yesterday we saw the hot wire anemometers in 3 modes of operations, that is constant current mode of operation, that is this is a hot wire anemometer where we have this wire here. This is the wire of few microns diameter, it is taken inside, the connections are given inside. This was used as wire is used to sense the flow. Here that is we saw 3 modes of operation. One is constant current mode of operation, constant temperature mode of operation, and another one is automatic adjustments with automatic control, that is with feedback. This is what we saw yesterday. In maintaining such hot wire anemometers, one is supposed to clean this wire periodically. Otherwise, what will happen? The dust carried by the flue gas, will get deposited, and we will find the heat transfer coefficient H. We saw yesterday the equation I squared RW is equal to H into A into TW minus TG. That is the equation, heat transfer equation, that factor H is affected if you allow the dust to accumulate on the wire. So what is to be done is it should be cleaned periodically so that the calibration curve is valid. Yeah, we also saw the calibration curves. In doing so, since the wire is so thin and short in length, it may break also while we handle it. Or if the gas flow which is there in the pipe may also contain some hard particles, and due to high velocity, when the hard particle hits the wire also may break. So in order to avoid this problem, what is done is people nowadays use a hot film anemometer. Instead of hot wire anemometer, they use a hot film anemometer. Here they take a wedge type glass. This is made up of glass support. It's a glass. Here what they do, instead of keeping a wire, they paste on both sides. This is a wedge type, just like a wedge type, and they paste the wire material, they deposit the wire material on both sides. It's a wedge, so it's and then take the wire. This is a front surface, and from back surface another wire will be taken. So now it's a hot film anemometer. Instead of wire, we are using hot film. Now it is supported on the face of the glass support. So naturally the breakage and all is eliminated. This is the advantage of hot film anemometer over hot wire anemometer. So now we pass on to the next method, that is the laser Doppler velocimeter. Here one can use either sound or light. The principle is making use of the Doppler effect. What is Doppler effect? Doppler effect states the scattered light from any moving body contains the information about the velocity of the body. So that scattered source will be also, that frequency will be different from that the starting from the source. So that is the Doppler effect, that is scattered beam contains information of the velocity. So that is expressed in terms of equation, frequency of scattered light or sound. We can also use either sound or light for this measurement. So f is equal to, that is scattered frequency, is equal to f0. f0 is the frequency at source 1 plus or minus v by c, where v is the velocity of the moving object and c is the velocity of the incident light or the sound, whatever we are making use of in a particular instrumentation. So plus we are using for the when the object is moving towards the source. This is the source from where we send a beam, that is a source. So if the object is moving towards the source, then we use plus, and when the object is moving away from the source. For example, this Doppler effect again used for locating for identifying the racing cars. Suppose the police officer will be standing here and he will send the light source or laser beam, whatever it is, and he will collect it back. So now this is going away from this is source. So here by collecting this reflected light or laser, he will find out what is the speed, whether it is more than the allowed speed in the road, that he will find out. That is the Doppler effect is used by the traffic police officers to locate the racing cars or the overspeeding cars or vehicles. So same principle here, it is because the moving vehicle contains velocity of it is being obtained here. Similarly here the v is the velocity of the moving object. Now in any gas flow or any fluid flow, that flow contains some foreign particles, and we assume that the foreign particle moves with the same velocity of the fluid. Under that situation, we send a laser beam with a beam splitter, it made into two, and with the help of a lens we converge it within the diameter within the diameter of the pipe. So where it converges, there may be a particle flowing with the same velocity of the gas, so it scatters the light. So this is the light and this is scattered light collected by another lens, objective lens, and through a pinhole we can control the intensity, and then it goes to the photomultiplier tube where the light is transduced into voltage. From that voltage contains the information of the velocity of the object. So that is it's an electronic circuit from which you, according to this equation, you will extract the information proportional to v, and that is being depicted as velocity of the fluid here. That is the principle of this laser Doppler velocimeter. So by focusing at different points, we can find the velocity of the fluid, and then we plot that velocity profile and find the average velocity multiplied with the area will give the flow rate. That is how the velocity laser Doppler velocimeter is made use of. It has got one main difference. Now we compare the pitot tube as well as hot wire or hot film anemometer. There the flow is abstracted. Here you have got only less area. For total area minus this area alone is available. That is the flow pattern is disturbed by inserting the pitot tube or hot wire anemometer. That is not there in the case of laser Doppler velocimeter. It is undisturbed flow. Without disturbing the flow, we are making the measurements. That is the main advantage of this laser this laser Doppler velocimeter. In aeronautics, in aeronautics laboratories, many places they use this laser velocimeter to find out the velocity of air particle in a channel, in a conduit. Next we go to the magnetic flow meter. One such magnetic flow meter principle, the sketch is given here. This is a magnetic flow meter. It contains a pipe made up of non-conducting material. This is a pipe made up of non-conducting material. It carries the fluid. Now here it can be slurries or the liquid containing some sediments also, because we don't have any obstructions. So slurries flow rate also can be made use of by this. That is the main advantage of magnetic flow meter. So we have got the non-magnetic pipe carrying the liquid perpendicular to in the direction perpendicular to the board, and by two electrodes we pick up the voltage developed in this fluid, which is put across north pole south pole of a permanent magnet. So magnetic lines are in this direction, magnetic lines are flowing in this direction. That is Faraday's principle. That is magnetic lines one direction, and the flow is perpendicular to the board, and the electrodes direction is perpendicular to both of them. That is now it's say if it call y, this y direction, this will be x direction magnetic lines, and the z direction is perpendicular to both. These are the flow the velocity of the conducting material. So the diameter of this pipe represents the length of the conducting material. Each small strip can be considered as strips. So it flows in this direction. Flowing direction is perpendicular to z direction. Magnetic lines is x direction, and the voltage developed is in the y direction. So we have got this equation: induced voltage EO is equal to, that is EO at the electrodes we pick up, B into L into V, where B is the magnetic flux density in Tesla, and L is the length of the conductor in meter, and V is velocity of the conductor, that is flowing speed, that is of the velocity of the conductor in meter per second. So the problem here is it's not as conventional conductor wire, but the whole diameter is considered as the wire length, as wire is in terms of disc, it moves. So the developed voltage is picked here. So proportional to velocity we have got output voltage, and the output voltage can be calibrated by sending known voltages, known velocities, and later on unknown velocities can be found out from this voltage developed between the electrodes. Here in this case, when the liquid that flows is non-conductive one, like just like water, the amount of voltage developed is very, very small. Then if you use the drift is a big use in a DC amplifier to amplify this voltage, the drift problem will come. For that, to avoid such a problem, what they do, instead of permanent magnet, they put a electromagnet of varying frequencies. Then the voltage developed also will be varying frequency at different frequencies, and that can be amplified in an AC amplifier suitably. Suppose if it is a conducting material just like liquid metals, then we don't require even DC voltage itself is sufficiently large, we can measure it by a ordinary DC voltmeter. It is to be noted, since it is a non-conducting material, the electrode goes into the body and touches the liquid at the surface of the liquid, then only the voltage can be picked up and it comes down. So this is principle of magnetic flow meter. Next we go to rotameter. For small flow rates and all, rotameters are used, both liquid and gas it can be used, but mainly people use it for liquid flows, rotameter. It looks like a conical jar with a tap, with a hole with some functions, with the height it will be there. The method of functioning is due to flow, the float rises. When the flow is there, it rises to different heights at a different flow rate, and where it stops, a measurement where it stops, that scale is written there, and that scale reading you can calibrate in terms of flow rate. This is the way it is made use of. The principle of functioning is, assuming that float is at some height, and let W be the load of the weight of the float, and buoyancy force equal to the volume of this float times the specific height of the liquid that flows, that is buoyancy force, that is weight minus buoyancy force, is balanced by the delta P is the pressure drop across this float into AF, that is projected area of the float, will be net force balancing. The remaining weight is taken up by the delta P times AF, that is the equation for equilibrium. Now you find for any given float or for any liquid, W is constant, B is constant, AF is constant for any given float and any liquid, given liquid. So when everything is constant, then delta P should be constant, but at the same time we find the equation for flow rate, Q is the flow rate through this rotameter, is given by A2. This is the A2 is the annular space. This both put together is called A2, annular space through which flow is taking place. CD is the coefficient of discharge, delta P is the pressure drop across the float, rho is the mass density of the flowing medium, and the A2 we have seen annular, A1 is the pipe, this is A1, the pipe inlet area. So in this, if delta P is to be constant, then whenever Q varies, all other things, this A2 by A1 and all, considering A2 by A1 too small, we can neglect it, and C2 is a constant. So you find Q is proportional to A2. Since delta P should be constant, when Q varies, A2 has to vary. That is the reason for different flow it rises, so that larger area is allowed, is there for the flow rate. So as it rises, area is increase at a linear rate. As the area increases as float rises in a linear relation. Linear relation is obtained by some parabolic curve, because if it is conical, then you will find area is no more proportionate to the lift. So some parabolic, some quadratic function, say way it should vary the profile. Hence you get area proportional to the lift. So you find Q is proportional to lift also. That is why we get some linear scale indicating the flow rate. So that is the way rotameter is functioning. It gives you a linear scale. As the flow changes, we measure the height and all. Depending upon the different densities of the fluid liquid, manufacturer gives different shapes for the float. Accordingly, we have to use it. That is given by the manufacturer. Before we pass on to level measurement, we see one more method for the flow measurement, that is called turbine flow meter. This is domestically used in almost all houses where it is to be the charged for the water consumption. If it is to be charged, then normally people go for such type of turbine type flow meter. It's turbine type flow meter. That is, in the pipeline you insert one turbine. Here it is shown. This turbine wheel is shown here with bearing and with webs. These webs is there. The radially probably three webs here, diametrically schematically shown here. 3 or 4 webs may be there, and between the webs it will be flowing, but the bearing is continuous. So it's a cylindrical piece. So that's how it is mounted. So you have got the turbine wheel blade made up of magnetic material. Yeah, magnetic material. So whenever a blade comes near this proximity pickup can be positioned outside the pipe carrying the liquid or water, and whenever a blade comes, this proximity pickup will give one pulse. Such pulses are counted in events per EPUT meter. It is nothing but events per unit time, per second or per minute or per hour. You can select. So many pulses per second. That is actually that is proportional to the flow rate. The counting rate, the pulse rate, is proportional to the flow rate. When we want to find out the total flow in a given duration, then you start the flow, and at the end of the duration, what is the total reading or total pulses, that represents the total flow. Total number of pulses represents total flow, and the pulse rate per second or pulse per minute or per hour represents the flow rate per second, per minute and per hour respectively. That is principle. Whenever it rotates to that extent, so if d theta is angular rotation, that represents small differential flow of dq. Then d theta by dt is the same as dq by dt. That is the counting rate. Pulse d theta by dt is given by the pulse rate. So this is the principle. If you don't have this proximity pickup, you can also go for purely mechanical counter also. So suppose this is a rod extended, and you can just connect a set of bevel gear and bring it out with a suitable sealing, and let it be counted here. This is mechanical counter. So it's a bevel gear unit connected to the axis of the turbine. The moment the rotation is brought outside by a set of bevel gears, and the second bevel gear axis is connected to a counter, mechanical counter. So here you can take the reading. This is what is used normally in houses. You will have the mechanical counter. The person will come in the beginning of the month one reading, and the end of the month one reading. The difference between two readings represents so many liters or so many gallons per month. So that is how it is used for making total flow or flow rate measurements. So here rotating speed, if you find out, then from the counter we can find out also flow rate also. So with this we close these flow measurements. Next we pass on to the last chapter in our topic, mechanical measurement, that is level measurement. First and foremost method is using floats. Floats are often used to find out, to sense the flow level of a liquid. And also we find in almost all houses we have tanks, water tanks, that water in the water tank is invariably sensed by having a float there. If the level is full, what will happen? This motion of the float is made use of to close the valve, that we can see the linkages. Suppose you want electrical signal, or if you want to just make a reading, you have a scale, the float end is connected to an extension rod, that rod end is moving over a scale, you can just make readings, so many meters height, water is there. Or you can also connect it to a potentiometer, resistance potentiometer, convert this level into suitable signal, electrical signal, and process it, and you can take it to a control room. Say in process industries, tank may be some distance inside the factory, that signal is brought to control room, the operator knows at any instant what is the level in that particular tank, it is given there. So float is the convenient mechanism, that is, it is a hollow plastic sphere, yeah, it's a hollow plastic sphere. So when it immerses, its weight is going to be very small, and even small immersion is sufficient to support this weight, and any further rise, it will push this float up. And you might have felt if you just raise to push this float up, it will sufficiently big dimension, you find lot of force is there. That force is more than sufficient to actuate a valve and close the water inlet into the tank in case the tank is full. That is a very convenient mechanism. That is more or less in open vessel we use these such type of floats. Suppose we have a closed vessel just like a boiler for steam engines, for example, or in power plants we have got boilers. Say if you don't have free service like this free service to atmosphere, we find immediately above the liquid level you have got steam at a very high pressures. So in such situations this type of float is not useful, but if it is medium pressure we can go for a side glass, it is called side glass. We can connect a glass tube to the tank so that the water level can be seen from outside. It is only for low and medium pressure of this vapor. If it is high pressure, then glass may not withstand. Then we go for the metallic tube connected to the main tank. It is called steel tube made up of metal tube made up of metal. Then we don't see it, since it is opaque, we do not see the level. Then we make use of a float with a bar magnet. Some bar magnet will be there as part of the float. So as the float rises, bar magnet also rises along with the float, and nearby we have a iron piece guided by a round piece where scale also is marked. So as the float rises, the magnet will pull the iron piece also to indicate the level. So wherever the float is there, the magnet attracts the iron piece and adjusts this level. As the float rises and goes down, the iron piece also will go down and up along with the magnet. So from outside we can see where the iron piece is there, and that is the level of the liquid there. So this is how in the closed vessels level is made, level is sensed or seen from outside. Another method is by using buoyancy force. Suppose we have a cylindrical member like that, and there is no liquid in this column, no liquid in the tank, then we find the load cell will give the total weight of it can be made up of any, it can be hollow and made up of any metal also, metallic hollow cylinder it can be. So cylinder weight will be indicated by this instrument, by the load cell, and that you will mark it as 0 level because full force is there. But as the level increases, we find the immersed volume, this immersed volume times the specific weight of the liquid is buoyancy force. So if W is the weight of the cylinder minus buoyancy force will be the reading here, load cell reading. So XO, this is our XO reading for load cell reading. That will be calibrated having known level, later on unknown levels can be read from the load cell. So load cell reading can be calibrated in terms of the level here, because buoyancy force is a function of is a functional level. So XO will be a functional level where W is a constant. That is how we use the buoyancy force to sense the level. Then we know when there is a liquid column, then the pressure at the bottom is a function of the column weight. This is a well known principle. By using that we have got some designs based pressures, by using pressure sense in different ways. Under different situations we can also sense the level of the liquid. One is at the bottom of the vessel we connect a pressure gauge. So we know pressure indicated in the pressure gauge is a function of height and the specific weight of the liquid, W into height. So for a given liquid W is constant, so P is proportional to height. So the reading in the pressure gauge is written, is calibrated in terms of the height of the column, height of the liquid in the tank. This is obvious method. Then second method, this is again open vessel. In closed vessel we go for the differential pressure pickup. This is differential pressure pickup. We have the vapor also of the liquid at the above the liquid. So the vapor pressure is taken to as one of the input pressure to the differential pressure pickup, and the bottom point, bottom near about bottom, it can be as small as possible, that point A. So total pressure at A at this point, that is PA, liquid column plus vapor pressure. So that is, so PA is equal to PV vapor pressure plus W into H. W is the again weight of the specific weight of the liquid here, and whereas PB, this point vapor pressure will be there. So PB minus PA, that is the reading, proportionate reading to the in the differential pressure gauge pressure pickup, is equal to WH. So these two cancels, PB minus PA, yeah, PA minus PB. So PA is larger, so PA minus PB will be equal to WH, both cancels, so WH, where the W is constant for any given liquid at a given temperature. So PB minus PB is proportional to H. So the reading of the differential pressure pickup will be in terms of the H, and later on we can use for any unknown H the reading. This is second way of using the pressure reading. Third way is using the pneumatic principle, that we call it flapper nozzle system. I once explained earlier flapper nozzle system. Flapper nozzle system. That is what is made. Flapper nozzle system consists of two nozzles. This is one nozzle here. This we will say the nozzle at the tip. Yeah, nozzle at the tip, and this is another nozzle. Yeah, fixer. We will call it fixer nozzle. Fixer nozzle. See, as per the flapper nozzle system or principle, the pressure in between the two nozzles, we call it chamber. This we call it chamber. The space between the two nozzles is called chamber. The chamber pressure depends upon the resistance for flow at the nozzle at the tip. That is the principle, an inversion or an application of flapper nozzle system. So at this point, whatever the pressure here is equal to, again if H is the height, that then pressure P is equal to W into H. That is the pressure. If the chamber pressure is just above the liquid pressure at this tip, then the gas will escape in terms of bubbles. So until you note bubbles, adjust the supply pressure with the valve, just rotate it. So the higher and higher pressure will be allowed, and the pressure in the chamber will, through the fixer nozzle, the pressure will be, liquid, the gas will be entering, or air, pressure air also, pneumatic air we can use, say preferably 1.2 bar pressure gauge if we have, you can adjust it so that different pressures can be allowed, and when the pressure builds to the extent of this pressure due to this column, then it will start, just at the time stop adjusting it and note down the chamber pressure in the pressure gauge, and that you can calibrate in terms of the known height. Later on any unknown height can be read in this scale. So pressure gauge will be calibrated in terms of height of the liquid above the tip nozzle at the tip. So these are the three ways in which pressure can be made use of, pressure of the liquid column can be made use of to sense the level of the liquid. The other one is capacitor. Any liquid or any solid or powder material will have its own dielectric constant. It is called dielectric constant. Dielectric constant. So we know in a capacitor, capacitance equal to area into the it is proportionate to, capacitance proportional to the area of the two parallel plates. This is two parallel plates area, and the dielectric constant of the material divided by d. This is the distance is d. We know capacitance is a function of all these things. Now here the area and the distance are all constants. This is electrode is one plate, and the tank is the second plate for the capacitor. Now when the charge or the liquid or the whatever the level, powder or whatever the liquid level is increasing, then dielectric constant is varied. This is what is varied. But in the two plates, the dielectric medium is level is changed. Hence you find dielectric constant for that capacitor made up of this electrode and tank will change. and this will form one capacitor in a simple circuit, electronic circuit, electrical circuit, and proportionately you can get a signal output from the circuit. So as the level changes, epsilon changes, capacitance changes, then voltage output corresponding in the electric circuit will change, and from that we can get a signal proportional to the level. So to insulate these two plates, we have got this insulation. This is one plate, this is another plate, because that in between you should do insulation, we have got insulator. In case the liquid is also contain liquid or the metal powder is a conducting material, then extend this insulation for the full length of the electrode, If it is a non-conductive one, it is sufficient if you insulate only at the top where the electrode and the tank are insulated. But if the material, the liquid or the gas, liquid or the metallic powder, whichever is stored there, is conducting, then extend this insulation throughout the electrode. Then you will have again the variation as per the level, the dielectric constant will vary and you will get the signal. That is the capacitor principle for the level measurement of the charge inside the tank. The last method is shown here, that is by using hot wire resistor elements. This is mainly used in the cryogenic liquid, cryogenic the fuel. So suppose in a rocket that before I mean at the time of manufacturing of the rocket itself, we will have the tank to store the fuel, liquid fuel, and in filling the liquid fuel in the tank, we should be noting at different stages of the filling up the fuel, liquid fuel, what is the level that is in the tank. To note the level of the liquid fuel in such a tank, such tanks in rockets, people normally go for this hot wire resistance element. There at the wall of the tank you find the resistance elements at different heights. This is one element, then you will have some gap and another element like that. So it can be as small as possible. Every say 1 mm you can embed such resistances, and resistance will be open to the liquid and it will be inside the wall, but element alone will be exposed to the liquid. So as the liquid level increases, for example at this level, two resistances are immersed in the liquid, and especially when it is cryogenic situations, you find the moment any element is immersed, previously we will say it is switched on, the current is flowing through all the whole resistance embedded will form one of the arms of the 4-arm bridge or Wheatstone bridge. So before filling up, we find the current is flowing through all the these resistor elements. They will assume certain due to current flow, it will attain certain temperature. So as soon as any element is immersed, then heat transfer coefficient of the element will drastically increase, and thereby lot of heat will be given to this liquid, cryogenic liquid, and that element resistance will come down. And that means previously if you have balanced it with any liquid, at the moment one element is immersed, immediately the balance is affected to that extent, and you will have an output voltage. And similarly number of elements when are immersed, then it will be multiplied, so many times it will multiply approximately. If you assume linear relation, then the output voltage will proportional to the number of elements immersed. So you can calibrate that reading in terms of the level of the filling up of the liquid fuel. That level you can always get in terms of the output voltage or imbalance voltage of the bridge. So this is a bridge, this is one of the arms. So if you call it R1, R2, R3, R4, and against 2 terminals to your power supply, the other 2 terminals you take the output. This is a typical 4-arm bridge circuit. So the hot wire resistance element. These are the few methods used for level measurements, though there are many other methods. These are conventional found methods. So with this I come to the close of the whole subjects, mechanical measurements. Thank you.